a probabilistic process with simultaneous polymerization, the chain degradation, and epimerization.
Okay, good morning, everybody. First of all, I want to thank Axel for inviting me. And I also want to introduce myself briefly because I think I'm a little bit exotic among all these outstanding scientists here. I'm a chemist, a simple chemist, and I've worked in the chemical industry throughout my professional life, mainly in an analytical laboratory. And when my retirement approached, I was looking for something which keeps my brain working and in shape. And I combined my interest in computer programming with my interest in prebiotic chemistry. And so it's only since my retirement 3 years ago that I developed some activities in this field. So I'm quite a newcomer, and I'm glad to be here. It's my first contact with the scientific community. While it's a bit complicated, I have at home a version of PowerPoint, but it only works with Windows 3.11. It refuses to be compatible with this newer systems. So I have misused Excel for the presentation of my slides. I have to see. So people often believe that the emergence of life has evolved purely by chance. They think that random events are involved, and if we think of random events, we believe they may happen or they may not happen. So we know that life has evolved, but it may also be that this planet would be a dead planet forever. I think this is not true. And I prefer the statement that the emergence of life is based on probable events. Probable events do happen, only the time at which they happen is random, and their frequency is determined by the probability. So from this point of view, I think the emergence of life is deterministic. Life must evolve if the conditions are given. And that's also the reason why I'm interested in probabilistic theories. My first paper appeared 2 years ago, and it described a process which is very similar in chemistry to the APED process of graphite. So it's a cyclic process, and we have 3 phases: a polymerization phase, in which peptides are formed having random sequences with respect to RNA configuration of the residues. And these residues are supposed, or they have a certain probability that they contain substructures like this, where we have a homochiral strand to which an antibody is linked. And these substructures are supposed to epimerize so that the extended homochiral sequence is formed. So this corresponding is placed. And that's of course true for the R series as well as for the B series. And if this has happened, all the peptides are hybridized again, and we get monomers with retention of configuration, and then the next cycle can start. And these phases are supposed to proceed in a sequential way. So the number of such structures now fluctuates around the expectation value. We have a binomial distribution, and this has a certain standard deviation. And so we get slightly different numbers of R and D substructures. Now, if all these substructures epimerize, then the number of epimerization is identical to the number of substructures. And since we have here a slight difference, and if hydrolysis proceeds with potential configuration, we have after the hydrolysis a slightly enantiomeric excess in the monomerase. And this excess is then fortified in subsequent cycles. We can simulate this process with a small computer program, and then we get this picture. Here are the number of cycles, here is the logarithm of the enantiomeric excess, and at the beginning we see here some scatter, we have some noise. The system does not know whether it should come left-handed or right-handed. And after some time, one enantiomer wins, and we enter an exponential phase. And once one enantiomer has decreased or has disappeared, this growth, of course, comes to an end. And this is close to 1, or this is a logarithm. And so we attain full homochirality.
So there are certain parameters in the model, like is there an activation step is one question, and
well, of course, the polymerization has to proceed by some mechanism, but I think that's not relevant to this model. It may be an NCA compound, or it may be catalyzed by minerals or something like this. It really doesn't matter. Well, but this cycling process has a disadvantage. Well, I told you that the phases are supposed to proceed in a sequential way, and I think that's very much unlikely in a prebiotic environment. I think it's more likely, or it must be that hydrolysis reactions and polymerization reactions and epimerization reactions proceed simultaneously according to the reaction rates. So I have changed my model, and so let us look at this scenario. We have a population of monomers, racemic monomers, RNP, and we allow for chain elongation by monomer addition. We exclude combination of different peptides, so chain elongation is only affected by addition of monomers. And when such peptides are formed, they may also be hydrolyzed simultaneously. We assume that the hydrolysis probability is proportional to the number of peptide bonds, and that the addition probability is proportional to the number of monomers. Now we know that hydrolysis of peptide bonds is very slow, so I have introduced a factor Fa, which defines the relative probability of addition reactions compared to hydrolysis reactions. That is, if we have equal amounts of peptide bonds and monomers, an addition reaction is by a factor Fa more probable than a bond cleavage.
But the point is that you need to activate the amino acid called F in the form. And the question is, this may be also a very, very slow process compared with hydrolysis.
Well, I have to make some assumptions in this model, and I choose this one. Of course, you need some activation to affect the polymerization.
Then the question is how you activate amino acid, because if you want to compare the rate of hydrolysis versus the rate of addition, it might well be the rate of hydrolysis may be faster if you don't have an activator in the environment.
Well, I understand that hydrolysis reaction or peptide bond hydrolysis has a half-time of a couple of 100 years.
What about the activation?
And activation, well, if it's a process like Raphael wants, I think it might be faster. But it must not be, but it
So because of energy, you can imagine that it can polymerize faster.
But of course, the system also works if FA is as fast as cleavage. Well, I have made, this may be a variable, and I have made some assumptions which I just showed now. But of course, other parameters, sets of parameters also work.
I mean, the whole model works only because of hydrolysis in the end, because if you didn't have that, you would never reach.
Well, I have a closed system, and I need to recycle the monomers to affect some sort of development.
So in fact, this rate can be high. It can always be high. Hydrolysis can. Okay. Very good.
Yeah, but conditions depend very much what other different conditions.
But even if it's infinite, it works. Even if it's infinite, it works.
Yeah.
And it's only if that one walks very, very slow, then it becomes rate determining. But that's not the case.
Okay, now I have simulated the scenario by a computer program. I input a number of monomers and this addition factor FA. And the monomers are symbolized by L and D strings, and these strings are stored in an array. Then the system generates a random number which comprises the combined probabilities of additions and hydrolysis reactions. And if this random number is smaller than the product of FA and M, where FA is an addition factor and M is the number of monomers, the program branches to an addition subroutine, and a random monomer is selected and added to another random monomer or a random peptide. And if this random number is greater than this, the program branches to a hydrolysis subroutine, and a random peptide point is selected, and the corresponding peptide is split into two parts. Then the array is reorganized because we have different amount of particles, and M and B are recalculated, and then the next loop starts. So let's see what's coming out. Result. At the beginning, we have only additions because we have only monomers, and the number of monomers drops very sharply, and at the same time dimers and trimers are formed. And when higher oligomers are emerging, then these decline again. And after some time, the system enters a steady state in which hydrolysis reactions are balanced by addition reactions. I have used an addition factor of 100 throughout my calculations, but that's very arbitrary. So this is the chain length distribution of such a system with a lot of dimers, a lot of trimers, and the number of higher oligomers drops sharply. If we calculate the average molecular, or the average residue number, we arrive at a number of 3 about. And if I change this factor, not very much happens actually. The number of residual monomers is reversely proportional to this factor. So if I increase this to 1,000, let's say, then this one here is reduced by the factor of 10. But the proportion of the oligomers does not change very much. That's of course, the reason of this is of course, if I reduce this by a factor of 10, if I start with 1 million monomers, I will have 3,000 residual monomers. And if I reduce this to a lower number, then I can only create very few additional peptide bonds, and the number of oligomers remains almost constant. I have now to look for the next slide. Pushing the height.
Yeah, maybe that's yeah, right. That's it. Stop. And now go to
Now
take.
take this one.
Well, you have it now, I think.
No, this is just to move the picture here. Not but using those slides. Now let us introduce epimerization. There, of course, also is a certain probability that substructures of this form are present. And these are supposed to epimerize. I have written the terminal end to the right side, which is not really according to the convention, but okay. So we get again epimerization of the terminal structure. And now I have to amend my computer program. I have to introduce a third branch, which accounts for this epimerization. Epimerization, in analogy to the hydrolysis, is supposed to be proportional to the number of substructures and to a epimerization factor, which is also arbitrary. So the random number I generate with the program must comprise the probability of addition, hydrolysis, and epimerization reactions.
Why the mutation should always go in the same direction? Because if we have two amino acid residues which are not one to another, in principle optimization can go in both directions. So the ability to prepare, to transfer, let's say, short peptide in the polyol completely will take a long time.
Well, the idea is that the extended homochiral structure is thermodynamically more stable than the heterocycle. So that the process goes from the heterochiral side to the homochiral side.
Yeah, this is true, but the question is, mechanistically speaking, it must be asymmetric induction in the sense that if you have one chiral center of one kind, it may affect its zero center to convert, let's say, from one to the other. But if you have two centers which are not touching each other, then they don't know one of the other, and then you might have reversible part, and this may take this process to go to the poly-A or the poly-B may take a long time. Understand the thermodynamics is not stable. The question is what is the kinetics, how this process will occur.
Well, I don't get the point really. Well, I think that an extended homochiral strand is more stable. So I have a certain driving force to induce this epimerization. And it may be that it's hydrogen bonding, or if these substructures are long enough, maybe that also secondary structures may be formed. Of course, it may also be the reverse reaction, but I neglect this. Then, more or less, the number of epimerization is decreased. Also, the reverse reaction is possible.
You're taking only thermodynamical models, but not taking into consideration the kinetical process, how this will actually occur. And since you might have two residues which are not touching, not in good proximity to each other, now you might really go to different directions. So this process may take a long time. I don't know whether it's some kind of an experiment where people are trying to do this randomization.
Well, the only literature I know is that this terminal epimerization is used for fossil dating. In this case, but of course we have the reverse reaction. We start from a homochiral strand,
Yeah.
and this terminal residue epimerizes, or racemizes more or less. But I think this reaction, which I claim here, should be more probable because of thermodynamic
There's another
reasons.
problem which is very important, is the solubility. The homochiral one after 4 and 5 are less soluble, whereas the one which are heterochiral.
Well, but I have
after
very short peptides only. If you remember my peptide, my chain length distribution, I think they do not become as long. And they are not really homochiral. Let me go back to the last slide. See, this still contains no residue. And if not 4 repetitive or repeat units are required, but only 3, there may be also other rests here. I only consider the substructure, not the whole peptide.
Excuse me. You know all the concentration of all individuals of peptides to do that. You know that you have. What do you know in your system? Don't understand. You have a list of all the possible peptides and the concentration of all peptides, and you look at all the possible reactions, or what are you doing exactly?
No, I have a
Yes,
chain length distribution which I showed,
Yeah, okay,
which
but
is
if,
determined by the addition factor. And
yeah, okay, I understand if you have only one monomer, but if you have 2
only
monomers.
those peptides
Mm.
which have this substructure.
Yes.
In this case, 4 homochiral residues to which an antipode is linked.
Mm.
Here it's for the D series, here it's for the R series. And only these react.
Yes, but what do you know in your systems? What are the compounds that are described in our model? You have all the possible combination, LD, LD, and
Yes,
LDD.
yes.
Oh yeah, you know the concentration.
Yes.
But okay, but it's the law. Up to which length? So if you know you can't stock all the possible concentration of all the possible reactions.
Addition and parallel to that hydrolysis.
Mhm.
So the length of the peptides is
Yeah.
limited because the longer the length,
Yes, okay,
the
but
higher the probability of hydrolysis, and they cut again.
okay, so you put a limit.
No, well, the limit is defined by the steady state of the system.
Yes, but how do you know the quantity of LLD? What is the quantity of the LD, LD, etc., etc.?
That doesn't matter because these particles, they don't react. Or they are supposed, they only can be hydrolyzed, or they can another monomer can add, but only.
How do you know, for example, the quantity of the LDDDL? If you
Well, that's binomial distribution. I show you that.
But that's the initial condition, right?
Yes, yes.
And then it's evolving.
Yeah, but still we get a binomial distribution even if it's
Yes, but the binomial distribution
show you
was
this.
with only one monomer.
You just got a box with 10 to 6 particles in it, and you know what all the 10 to 6 particles are. You said you store the strings within each.
Well, the probability, the formation of such a structure
Okay, but what?
is proportional to the mole fraction of D to the power of the number of repeat units and proportional to the mole fraction of R. So if you have the mole fraction, you can calculate this, and if you know the number of particles which have a chain length greater than the repeat fraction, number plus 1, then you can calculate the number of these substructures. So, I have this amended computer program. We have this additional branch, and after this branches according to the random number which is generated here, and after one of these branches has been used, the array is again reorganized, and M is the number of monomers, the peptide bonds, and the number of substructures, and the mole fractions are recalculated. Now, if you run this program, you have a very similar picture to the one obtained by the cyclic process. We have here a random phase, in which we have a lot of noise. Again, we have oscillation between L and D configuration, and then the system enters an exponential phase and reaches the final phase, which is characterized by the definition of one enantiomer. If we have a look at some arbitrary segment and look at the equalization steps, we get this picture. It's a typical pattern of a time-dependent occurrences. We have here the L equalizations, and we have the D equalizations, and we see that the intervals between two equalizations vary, and also the number of D equalizations and L equalizations in this arbitrary segment is slightly different. And of course, it would be different if you compare this setting with another segment. If we determine now the distribution of the equalization intervals, we get the typical exponential distribution. And with this set of parameters, the mean value is 468. That is one reaction step out of 468 is an equalization. Is a de-equalization, all the same is true from equalization if we start with a racemic system. So, if we do not look at the equalization intervals, but at the number of equalizations per segment, then we get this distribution. Usually, the distribution of a time-dependent occurrence is a Poisson distribution, but according to the central limit theorem, that passes over to a normal distribution. And I have here selected the segment size for this set of parameters of 46,800. That is 100 times the average value. So I expect a mean value of 100 equalizations in this segment and a standard deviation of 10. And that's exactly what I find with my computer program. So this is also the reason why this continuous model is so similar to the cyclic model. In both systems we have a normal distribution of the equalizations. In the cyclic model, it is caused by the distribution of the substructures, and in this model, it is caused by the number of of epimerizations per segment. So a segment is a continuous model, has almost the same properties as a cycle in the cyclic model. So with this knowledge, we can devise another computer program and abandon this time-consuming handling with strings. But we need two additional tools. One is we have to know the frequency of epimerizations independent from the mode fraction. So this is the equation. This is my segment size. I have defined it 100 times the mean value, the expectation value of the epimerization interval if I start from a racemic mixture. And this is the epimerization interval if R is changed. And this can be calculated by this equation, and you see you need the expectation value of the substructures. That's quite a problem because the epimerization disturbs the system, and you can't use the standard binomial equations. But I find that when I run my program, that the probability that in one reaction step a substructure is formed is exactly equal to the probability that a substructure is destroyed. So I have also here a steady state. And I can analyze the processes which lead to the destruction or the formation of substructures. During addition steps, a substructure can be formed by addition of an optical antipode to this precursor. I call this one a precursor. Or it can be destroyed if some modulator is added to a substructure because it's not terminal one anymore. During hydrolysis steps, the substructure can be created if I cleave an appropriate peptide bond, and it is destroyed if I cleave a peptide bond which belongs to the substructure. And also epimerizations, of course, destroy substructures. And each reaction has a defined probability, and I can derive an equation from this. And this is this one, where K is the number of peptides including monomers, N is the repeat unit, F is the epimization factor, E is the number of peptide bonds, and D is the mole fraction of the D intermediate. But still I have a problem. I need to know the expectation value of the precursors. And as you see from this slide, precursors can be formed from substructures, and substructures can be formed from precursors. So I have an interdependence, and I need one to calculate the other, and that's quite a problem. I've solved this problem empirically. I just used my program and counted the precursor structures independent on the mole fraction now. And what I get are these curves, they're exponential functions. The lowest one is which I would expect if no epimerization occurs. That is just the number of particles which have a chain length equal or greater than the repeat number, times the mole fraction of R residues to the power of a constant A. In this case, A is 4 because I have 4 repeat units. And if I introduce epimerization, this exponent decreases, and I just use this as an empirical value, and then I can solve this well, doesn't want to. I can resolve this equation because I have this value. So the other tool I need a means to convert or to generate random variables which have standard normal distribution. I can achieve this by using the normal cumulative density function, which is this one, and just exchanging x and y axis. So this corner comes to here, and this comes to here, and I get this curve. And I used 4,000 discrete integer values, and then I assigned the appropriate random value to it, so I have 4,000 data pairs. And if I generate a random number in the range of 1 to 4,000, I can transform the uniform distribution of random numbers, which the computer generates, into a normal distribution. So now I have the tools to devise the new computer program. I input the parameter set, number of molecules, addition factor, dimerization factor, substructure, sequence size, and the system calculates the chain length distribution, and it calculates the expectation value of the dimerization frequencies. And these frequencies are modified accounting for the standard deviation, and after that the mode fractions are recalculated and the expectation values of these frequencies. And then the next loop starts, and if the mode fractions exceed 0.95, I stop the program. And this is really a fast program and can be used up to monomer numbers of 10 to the power of 25. But of course, then you have to increase the sequence size. In the next slide, the result of this program is compared to the original version, and you see it's almost the same. So I think this new program reflects the situation in the correct way. With this program, you can also see what happens if I apply an initial enantiomeric excess and switch off the part of the program which is responsible for the variation of the standard deviation. And if I do that, the system starts directly with the exponential phase. So it's a typical antagonistic process. Enantiomers grow on behalf or at the expense of the D1s through the epimerization, and vice versa. And if one of the enantiomers is greater than the other one, we get this exponential growth. You can also separate the antagonistic value from the random value, and during the process the differences between the expectation values of the frequencies sums up and causes the expectation term, and also the differences of the random variables, they sum up I call this random term, and the product of this with the standard deviation is random term. And if we have a closer look to the random phase, we get this picture here. The red line indicates the sigma border for the random term, and these curves are the random terms. You see they develop here slowly. They may be in one part of this diagram or in the lower part. They also may change from one side to the other, and they have a strong influence on the expectation term. If they run on this part, then the expectation term moves in this direction, and we get an up system. And if the random term moves in this one, here we have a Maverick that crosses this border, then the expectation term moves in this direction, and we get a D system. And if it turns from one side to another, in this case, for example, also the expectation term may change its direction. I have defined the end of the random phase as the point where the expectation term crosses this border, and at this point the final configuration, stereo configuration, is determined with a very high probability. It is a characteristic of this process that this random phase, as the duration of the random phase, is a broad distribution. We see here some systems which attain the exponential phase in a very short time, and some which need up to 6 times as long. And this might be interesting when we have a look at the propagation of the electromagnetic sets. So if we, for example, assume that several adjacent systems develop independently and they spread, then the most advanced may force its stereo configuration on to the other ones. I would like to present some results. Here we have the polarization factor. Here is the repeat unit of the substructure. And we see that the duration of the whole process is a function of 1 over Fe, linear function. And if we consider the dependence of n versus direction steps, we get an exponential distribution. That is, of course, caused because the probability of formation of a substructure decreases very much if you increase the repeat unit. And you also need longer peptides, and as I showed in the peptide distribution, longer peptides become very rare. We can visualize this in this slide. The process runs the faster, the steeper the slope at this point here. We start from a racemic mixture, and if the increase, this is the mole fraction R, and this is the frequency, polarization frequency. So if the polarization frequency increases very fast, if R is increased, then we have a very fast process. If it decreases, the process takes longer. I also added the curve for n equals 1, that is, we have structures like this, RP, and this may be some arbitrary rest. then we have L equals 1. And then we have a slope of 0, that in this case no anomeric excess can be developed, and the system remains in the reciproc state indefinitely. All that is clear if we have a look at the equation. The probability of substructure formation is L to the power of n times d and some constant. And for the d substructures is d to the power of n times L. And if n is 1, then we have equal probabilities and we don't get any bifurcation. If we increase the number of monomers, of course the number of reaction steps increases. The more molecules you have, the more reaction steps you need, and it's almost proportional to n with a slight exponential component. Well, these reaction steps are not very informative if you want to translate it into time, but I'm not a kinetic expert, so I didn't do that. But the process is certainly not very fast. I think it may take a couple of thousand years to complete. And there may be means to reduce this duration. First of all, it would be quite valuable to know to have some experimental data on this epimerization. Is there dependence on the repeat number? Does it also work if n is 1, then this model doesn't work? And we can also speed up the process if we do not consider terminal enantiomers linked to a homochlorous strand, but also internal ones. I think also these should have a thermodynamic advantage and turn around to the homochlorous strand. And if we increase the number of substructures, we also increase the process. And there's of course a certain probability that you get homochlorous peptides, and it will have a certain length. They may have enzymatic properties, and if they can speed up epimerization, addition, or hydrolysis, we also have a speed up of the process. So we have another autocatalytic process superimposed to the one I have just presented. In this context, it's also quite valuable to know the influence of stereoselectivity. If you have a certain selectivity, and this described in the literature, you increase the probability that you create homochlorous peptides, and then you may have more enzymatic molecules. And one disadvantage of the model is, of course, the low average value of the chain length distribution. If you increase the average chain length, then you have more peptides, which is the minimum chain length, and you have more substructures, and also this would increase the process. So there are some points which could also be investigated, and I have come to the end, and I thank you for your attention.
Okay, so was there some questions? Yeah.
I have a question about your method of respiration. when the clarity generation, occurs, before very at the beginning of the early stage, you see some random oscillations. What mechanism makes that kind of oscillations before the onset of the transition?
If I start from a racemic mixture, I have a certain expectation value for the substructures. Let's say it's here, scale, and we have a normal distribution. So now let's assume the actual R value is here, and the D value is here. So we have a difference between R substructures and D structures. This is probabilities. So now, just remove equations. There's these probabilities. And if L is larger for D, this probability is higher than this one, and also the expectation value in the second segment becomes higher. So for the log, maybe shift it slightly here, for the D, maybe here. So this is the expectation value L in the next segment, and this of D. Then I have, of course, again, this normal distribution. And now I again calculate the number of substructures, and it may be, let's say here, maybe reverse, the D is here, and R is here. And so
What are exactly these curves? I don't really understand.
these are the normal distributions. So
Of
if
what?
you have an expectation value,
Yeah, but distribution of what? What is exactly?
this is the expectation value formation of such structures. Well, I should say that this belongs to the cycling process, where you just build up your substructures from monorails.
Mm-hmm. Yeah, but the substructure are just from the. You have, everything is from the beginning, so you don't destroy and construct back. Don't get exactly what you're doing.
So as page 5 or 12, you show very large fluctuation before at the very early stage of the transition to color.
So what I want to say is D and R may be changed so that the initial enantiomeric excess may be reduced or enhanced or also inverted in a consecutive cycle.
Why this kind of thing has happened? In my talk, I said there are two steady states. One is unstable and the other is stable. But actually, there is another kind of steady state that is excitable state. An excitable state is a state that if the perturbation level is below the critical value, it is stable. But if perturbation exceeds some critical value, it is unstable, then transition occurs to the other state. So in your case, excitable state, racemic steady state is excitable state. So the fluctuation is generated randomly. So before the emergence of fluctuation above the critical value, it random fluctuated. But if once random fluctuation exceed some critical value, then transition occurs. Am I right?
Well, this critical value may be the crossing of the
You continuously
application
add-
term with
You continuously add fluctuation to the computer simulation.
Maybe it's a Monte Carlo simulation.
Yeah.
So you have a finite, maybe there's a finite number of molecules. Is that? You have finite number. You have not. It's not a continuous model. You have just.
it's a closed system.
Yes, but for continuous variables, you have I don't know 10,000 of L, 10,000 of D, and so you have this quantity of LD, this quantity of LD, etc., etc. Is it that? I understood exactly what are your parameters actually.
At the beginning, yes, but if you have ephemerization, you have different amounts of ephemerization, so
Yes.
you change the number of enantiomers.
So yes, you will. But okay, what are your parameters you are tracking? You know the number, exact number of L, the exact number of D, the exact. What do you know, and what are your parameters?
The parameters I use is the number of amino acid units
Yes.
and the addition factor, which I only need to define the chain length distribution. Had nothing to do with the ephemerization. Then the ephemerization factor, which defines or is the parameter for the frequency of ephemerization. The repeat unit of the substructure.
What do you mean by the repeat unit?
I have made this a variable, so I have calculated the whole thing for, let's say, substructures which have 4 or 5 or 6 homochiral units.
You mean that? Okay.
So, well,
You mean you can evaluate the number of homochiral structure, and how do you know that?
let's say we have a certain repeat unit, it's 3 here, it's 4 here, and it's 5 here.
Yeah.
I've done this because I don't know how fast such an ephemerization occurs. The longer I think, the higher the probability that ephemerization occurs, because you have to feel in thermodynamic, they are thermodynamically more favorable.
So you have a parameter that is tracking the number of G, the number of tetra, etc., etc. But how do you? But once you have the polymerization, how do you know how many 3, how many 4, how many 5, etc.
Yeah,
are there?
yeah.
It's quite
I know,
difficult.
I know how many particles in my chain length distribution have, let's say, 1, 2, 3, 4, 5, 6, 7 residues or more. And from that, I can, of course, calculate the amount of these substructures.
Is it simple to do that?
Yes, very simple.
How does the addition of the proteins depend on the chain length? The addition of monomers to the polymer. How does it depend on the chain length?
No. I just assume that it's random, and there's no difference between the reaction rates, and also there's no difference in the hydrolysis rates. It's independent on the length of this peptide. And
So when you look at a branched polymer, all processes would go a lot faster. Because then the number of ends in the polymer increases the size.
Could you please go back to the last slide, open question? Yeah, I would like to discuss a little bit this question. I mean, the lengthening of peptides. Can Can I?
Short, because that's the
Four, yes. Four. Thank you. I wonder, I don't know if you publish some experimental part of your PhD, but I remember that in your PhD you show that the pK of that's a pK of amino acid. It's about 9, and the pK of peptide, when the lengthening of peptide, when the peptide become larger, the pK become from 9 to something like 7. And so now, if you add this to a graph in which that's the pH of the primitive ocean. If you have here, if this is 7 and this is 6, the pH of the primitive ocean was around 6, maybe less. In this condition, when you start from the beginning, I mean the amino acid at 6 is very is very protonated, and so if it's largely protonated, it's not a nucleophile against the carboxyanide. But if you have a peptide, longer peptide, at pH 6, longer peptide is not so protonated than the amino acid, and so the longer peptide become longer because it's more
better nucleophile.
Because it's more nucleophile than amino acid, and so this, in my mind, is one way to prove that when the peptide start, of course they do what they can. I mean, because they are alone. But when the peptide become longer and longer, they can go longer when they start from here. They go longer.
So what you suggest?
And the second thing is when you have peptide, many peptide, and a small amount of N-carboxyanide, really small amount. This is an initiator, and this is a monomer. But if you have a very small amount of monomer and large amount of longer peptide, you have no small peptide which are 4, but only bigger. So it's two ways which could explain the mechanism of increasing peptide.
So what you
yes?
What you suggest is that I make the probability of chain length elongation a function of the chain length itself. The longer the chain length,
exactly,
the higher the probability.
First, and second thing,
not only
the
monomer,
ratio monomer over initiator it's very lower than 1. And so with this both assumption, you can try to improve your
Yes.
So, are there other questions? Okay, so I think that we can stop now and have Coffee first, okay, yes, thank you. Okay, and we start back at